IP-XACT based SoC interconnect verification automation. Abstract. In complex modern SoC system on chips, is verifying the backbone interconnect with a large number of both master and slave is one of the most significant challenges. It requires verifying the various interface protocols, convergence of the different transition types, a large combination of transition paths. To cope with this problem, we use verification intellectual property (VIP) for each protocol and a verification platform for interconnect. However, configuring each VIP to connect them to the entire master and slave interface is a cumbersome process. It's also very challenging to update to each configuration to comply with the frequent specification changes that accommodate market changes. By automatically generating these configurations for the interconnect verification environment using IP-XACT, we can dramatically reduce the time and the effort required for SoC backbone interconnect verification. Introduction. To reduce the cost of the silicon chip, the SoC industry is trending to merge the various functionalities such as GPU, modem, Wi-Fi, and Bluetooth into a single chip or system-on-a-chip (SoC). Its complexity, as well as its size, increases rapidly. This causes that a backbone interconnect and the SoC includes a significantly large number of master IPs, such as CPU cores and other MCUs, and slave IPs, memories, or Bluetooth. Thus, it is challenging to verify the backplane, considering reachability, routing correctness in the memory map and address space, and deadlock-free performance validation, bottleneck-free, and etc. The dedicated backplane verification environment is required where it consists of the backplane RTL and the verification IPs, replacing real master and slave IPs. However, it is very time-consuming and error-prone to create this verification environment since each test bench is used to be coded manually and every master and slave IPs are configured individually. To overcome these challenges, the SoC industry shifted the paradigm for SoC integration from the text-oriented coding to IP-XACT, that is the metadata-based generation. After the cluster-level integration and full-chip-level integration are performed with the metadata, cluster and full-chip RTLs are generated instead of the manually coded. The IP-XACT meta used in SoC integration originally includes only the specification information required for the integration. To improve the verification productivity, the IP-XACT-based flow is extended to a package. The specification is necessary for the backplane verification into the IP-XACT efficiently and utilize the specification, the information to generate the dedicated verification environment automatically. In this paper, the challenging in creating a verification environment for SoC backplane verification are discussed. The approach to resolving them and the enhanced result to the automation are presented, followed by the conclusion. 2. Challenges in SoC interconnect verification. We've been applying the UVM-based verification environment setup to create a verification environment of the SoC backplane, as shown in Figure 1. And this environment to connect to VIPs to backplane interfaces instead of a real IP, we force the IP interface to connect to the VIP. For example, we force interface of the IP such as a host CPU, which connected to with the slave interface of the backplane to connect to the master VIP, and also force slave interface of IP such as a memory controller or prefers to slave VIPs. The use of the VIPs for the interfaces which have different protocol enables the generation of the transaction through the interconnect, which randomly covers the address space and interconnect route. In this environment, the protocol validation also can be hacked automatically by the VIP included checkers to verify the end of the the end-to-end transactions, it is needed to appropriate the system-level scoreboard. So we also install an interconnect validator VIP, which is a system-level VIP that monitors transactions within an interconnect fabric and performance checking if the transactions behave correctly. For VIP setup, we need to specify the various configurations for each VIP, such as a hierarchical location of the connection point, interface type and port name and list, and bit width of each port, and FIFO depth, multiple outstanding values. Also, we need to specify the spec of the SoC backplane, such as memory map, address space, decoding, reachability, and so on. To maintain these configurations efficiently, we used to have a spreadsheet-based tool which generates a test bench. In the spread-based flow, we have to make a spreadsheet as shown in Figure 2. For example, if we want to make an interconnection verification environment such as Figure 1, we have to describe configuration for 2 ACE master and 3 AIX master, 1 ACE slave and 1 AHB, and 2 APB slave VIPs on a spreadsheet format like Figure 2. The master interface configuration of the spreadsheet should include VIP types such as ACE and ACE, AXI3, and alert width and data width and ID width, interface name, and so on, which needed for the VIP configuration for the 5 master VIPs. We also describe configurations for the 4 slave VIPs on slave interface configuration table on the spreadsheet. The configuration also should include the VIP type, port width, name, and the address range which the interface has. Moreover, we have to describe the reachability from the master VIPs to slave interfaces on the master and slave mapping table of the spreadsheet. If a master VIP to a slave VIP is reachable, it is T for true or false for false. The once we specify the all configuration of the VIP and backplane of the spreadsheet manually, we generate a verification environment, and then we have to connect the generated test bench to the DUT. The port level connection of each interface between VIP and backplane is needed to be done also manually, so that a hierarchical location of each VIP instance and a signal mapping between the VIP instance and the actual DUT signal should be described as shown in the Figure 3. From above the procedure description, we can easily understand the configuring the entire VIPs and typing into the spreadsheet is not an easy job, since our SoC consists of hundreds of master and slave interfaces should be connected with the VIPs for interconnect verification. The amount of the routing information we have to define is multiplied by the number of masters and slaves. The codes for the connection of VIP ports and RTL ports we have to manually type in is also tens of thousands of lines. Moreover, during the SoC integration progress, SoC spec is frequently changed, which causes RTL modifications such as instance name and hierarchy, port name, or routing spec of each backplane component. These SoC spec changes needs to be applied to the verification environment also, and this work is not an easy job to comply every RTL change. It is a hectic, and time-consuming and error-prone process. And due to this challenge, the verification group faces many incorrect verification failures, which also result in a massive amount of waste of the engineering resources, and sometimes highs real design bugs. 3. IP-XACT-based verification automation. As mentioned in the introducing the chapter, our SoC integration process was changed from text-based to metadata-based flow, and the metadata is IP-XACT. Originally, we included the design spec information in IP-XACT. For example, an IP-XACT component for each IP include port list, bit width and bus interface, memory map, and register definition, and so on. In IP-XACT standard, there are a set of the schema for capturing spec of a bridge, that is routing information between its input interfaces, that is slave interfaces, and output interfaces, that is master interfaces for interconnect IPs such as CCI and AXI2 APB bridge. For SoC or a subsystem level interconnect verification, all interconnect component should have routing information. However, in the design integration flow, the routing information is not needed. It should be additionally added for interconnect verification. It is shown in the figure 5. The routing information in IP-XACT consists of the input bus interface and the memory map, the subspace map of the memory map, and the reference from the subspace map to output interfaces, the base address and the address space for the output interface. The description is quite complicated to express routing information for interconnect component with many inputs and outputs, and it's quite a burden to the IP designers. Figure 5, routing information for interconnect component. To resolve this complicated issue, we developed the automation script to package routing information into IP-XACT easily for the interconnect IPs. Most of our system interconnect, which are connected to the subsystem or our system level interconnect to subsystem, are automatically generated by a tool. In case of the embedded interconnect like NCCI, they are generated by the embedded generator such as embedded designer, and the generators also generate IP-XACT, which already includes routing information. Our in-house bus generators are also their routing information as text format. So our script converts to the text-based routing information into IP-XACT standard format and integrate into IP-XACT file for the component as figure 6. The figure 5, routing information integration flow with the routing information text. In case of the AMBA bridge like 1x16 AXI2 APB bridge, usually they are used to connect to system level interconnect with the leaf IPs. They have a full matrix form input bus interface to output bus interfaces. The address ranges from the output interfaces with evenly divided. For example, the 1x4 AXI2 APB bridge, which input address range is from 02 FFFF hexadecimal FFFF. The address space range for each output interface is 4000. For this kind of the bridges, the routing information can be added into input addresses range like figure 6. Figure 6, routing information integration flow for AMBA bridges. In the case of the one-to-one bridges, such as protocol changes like AX2 APB, the full range of the address for input interface is directly to map to the output interfaces. In this case, the routing information can be easily added by the script like figure 7. The figure 7 is the routing information integration flow for one-to-one bridge. In our last SoC project, routing information for 1 and 24 of 1 and 30 interconnect components are added by our automated script. For the last of the interconnect, we also used GUI-based routing information integration tool for designers who are not familiar with IP-XACT as figure 8. To make a routing information using the GUI editor, designers just click input slave interface to make a memory map and click output master interface to make address space with a range like OX10, 1000, and then click and drag address space to the memory map with a base address. Figure 8 is a GUI editor for IP-XACT routing information. That during the SoC integration process, each IP is instantiated in the subsystem, and each subsystem is also integrated into a top-level SoC. After the integration, IP-XACT data for each subsystem and type-level SoC already contain connection specifications such as port mapping and bandwidth, hierarchical structure of the SoC and configuration using the SoC IP-XACT data reachability using reachability routing and memory map from any master interfaces such as CPU to any slave interface such as DRAM or IP register path can be calculated in the connect verification environment, can be generated automatically by using this information. That we collaborated with the EDA and built this automated flow to generate interconnection verification environment without any human intervention. Using this flow, we just load IP-XACT for the integrated SoC design on the tool and the select master and slave interfaces which should be connected to the verification IP on GUI as figure 10. Then the all manual work of the configuration for every VIP and SoC integration interconnecting specification thus not necessary. The IP-XACT database includes each interface information such as hierarchy, prototype, master and slave mode, the port mapping, port width and routing information from any master to any slave. So it is not needed to check the design specification to update verification environment and the configuration verification environment and the port mapping manually. So when the SoC RTL is updated during the integration process, the SoC IP-XACT data is also updated and we can quickly regenerate interconnect verification environment based on the IP-XACT. The figure 10 is working flow and a GUI of the IP-XACT based interconnecting verification environment and generation. Result. Our recent SoC interconnect verification environment includes more than 50 masters and 400 slave interfaces which connected to the VIPs. It took over 2 weeks to create an initial version of the interconnect validation environment by the previous manual process. However, IP-XACT-based automation shortened this work into only 1 day. In manual processes, just end-to-end interconnecting instances, that is, if IPs interfaces was supposed to be connected with the verification IPs. In IP-XACT-based automation, however, any interfaces inside any hierarchical the level of the SoC can be selected as verification point to be interconnected to the verification IP. IP-XACT-based verification environment automation also enables to generate multiple test benches for subsystem or SoC and different test bench behavior. In our project, we can generate more than 5 different TB for SoC and each subsystem. These automation reduced time to the test bench modification to comply the architectural or design dramatically. So we also can generate a new test bench for every RTL update at the early stage of the project, which happens 1 or 2 times for every week. As a result, we obtained the less number of the false negative report time to run more tests, finding more interconnected bugs in the early stage of the project. Conclusion. In this paper, we introduced our experience for verifying complicated SoC level interconnect verification. We already developed the interconnect verification environment using interface IP, VIP and interconnect validated VIP, and the Excel-based automated flow. However, the configuration of every VIP to connect them into the DUT's entire master and slave interfaces is entire manual process. Moreover, it is very difficult to update the configuration to comply DUT specification change because the number of masters and slaves are enormous, and yet the DUT specification is frequently changed during the SoC integration process. Thanks to IP-XACT based on a design automation flow, design integration flow, we can get a much information from this metadata for interconnect verification environment. However, routing information for all interconnect components, which is needed for interconnecting verification, should be added in IP-XACT, and a little burden for design integration flow. So we developed a method to add this information for each interconnecting components. We can automatically generate interconnection verification environment based on the IP-XACT, and it dramatically reduce our turnaround time to set up interconnect verification environment. As a result, we obtain the less number of false negative reports and the time to run more tests, finding more interconnect bugs in the early stage of the project. Okay, thank you for your time. And it was the DVCON paper, IP-XACT based SoC interconnect validation, verification automation. Thank you.